Finally, on to the last couple problems here. Suppose a professor writes two types of exam, easy or hard. 90% of those exams are hard, and there's an 80% chance that the first question on a hard exam will be difficult, and 15% chance the first question on an easy exam will be difficult. Again, not sure exactly what I'm looking at. So, present probability statements very quickly. So, 90%. So the probability we get a hard exam is 0.90. 80%. 80% chance the first question on a hard exam. So we actually, if you look at that, um, the probability of a difficult question, given that it's a hard exam, is 0.80. The probability that the first question on an easy exam, so that'd be the difficult given that we have an easy exam, is 0.15. I guess at this point, if we know that 90% of the tests are difficult or hard, that means the probability of easy is 0.10. So the fact that I'm being given conditional probabilities, this should lead me directly down the road of setting up a tree. All right. So here are the two scenarios. We got difficult question and then difficult test or hard test. So the first split, as you can see from the beginning, the question level is based on the difficulty of the test. So hard versus a not hard test. And then we're going to go difficult question, not a difficult question, not a difficult first question, I should say. So 90% of the exams are difficult, 10% are easy. Hard test with a difficult first question will be 80%, which means 20% of difficult tests have an easy first question. And the easy tests, or not hard, right? This would be the same thing as not hard. 15% of these start with a tough question, which means 85% of the easy exams start with a pretty easy question. My recommendation to you guys will still be that if you take a quick second and fill in the end of the branches, that's probably going to make a lot of these other questions pretty easy. So hard and difficult. So 72% of this professor's tests are not only hard, but they also start off with a difficult question. 0.9 times 0.2, so that means that 18% of all of his tests are hard, but they start easy. 0.1 times 0.15, 0.015. So an easy test that starts with a difficult question is very unlikely. Only about 1% of his tests do that, and then about 8% or 8.5% of his tests are not hard and start off with an easy question. So once we have all those, we should be good to go. All right, so question A. On a given exam, what's the probability it is a hard exam that contains an easy first question? So really, the sample space we're pulling from are all of the exams. So this would be the probability that we have a hard exam and a not difficult question, right? They're not saying, given that it's a hard exam, what's the probability of easy first question or anything like that. They're saying, on any of the exams, what's the probability it's hard and it contains an easy first question. So this is a basic multiplication type rule. Hard and easy first question, that would be 0.9 times 0.20, and I've actually already done all the legwork on this. 18% of the tests are a hard test with an easy first question. Part B, on a given exam, what's the probability that the first question will be easy? So in other words, what's the probability we get something that is not difficult? Now, there are two scenarios for not difficult. Right here and right there. The fact that we've already done the legwork, again, just if you think about this, you can either have a hard test and not difficult, or you could have an easy test and not difficult. So hard test and not difficult, so that'd be 0.9 times 0.2, or an easy test, 0.1, with a not tough first question, 0.85. And when we put those together, 0.18 plus 0.085. So the probability that we get an easy first question, about 1 out of every 4 tests, starts with an easy question. Now we're going to get a conditional probability. Suppose the first question is easy, right? So now all of a sudden we've got this subgroup. Suppose the first question is easy. So we're given a not difficult question. What is the probability the exam is hard? So what's the probability out of all the ones? If we know we got a test with an easy first question, what's the probability that it's going to be a tough test, right? That might be something that would be of interest. You know, you look at the first question and you realize this is a tough question. I wonder if this is a hard test. So just run through your conditional probability setup. So this would be hard and easy first question over the probability of an easy question. Look at your tree, hard and easy first question, that was 0.18. Probability that we have a difficult first, or an easy first question, excuse me, not difficult. We actually just did this part in part B. I'm going to take advantage of the work I just did. Again, I just did the probability, right? I just did this probability of an easy question up here in part B. Right? It's sitting right there in part B. Take advantage of the work we've already done. So 0.18 divided by 0.265. So if the first question is easy, there's a 68% chance that this is going to be a tough test. And then are these two things independent? Easy exam, difficult first question. So I'll do part D right here. So is the probability of easy exam, which would be not a hard test, and difficult first question, right? Is that equal to easy test? So just follow your conditional rule, check a few things. So again, probability of a easy exam and a difficult first question over the probability of a difficult first question. So an easy exam with a difficult first question would be 0.015 if you go into that branch. And then there are two ways to get a difficult question. A hard test, so that would be a hard test and a difficult question. Or the other way to get a difficult question, this would be an easy test and a difficult first question. And 0.15 divided by 0.72 plus 1.5% is 0.204. Right? So there's my conditional probability. The probability we got an easy exam, 0.10. These two things are definitely not equal, which means they are not independent. So there is a relationship between if we get a hard first question and then what kind of test we're about to get. So last one, supposing your city, 37% are Democrats. So the probability we get a Democrat, 0.37. 29% are Republicans. Probability we get a Republican, we'll have two sets of parentheses there. Probability we get a Republican, 0.29. And 11% are other parties. Probability of other, 0.11. Voters not aligned with any of the others are termed independent. Well, quick check, right? Keep in mind that the probability of your sample space has to equal 1. And this is a good one to finish on because we can see 0.37 plus 0.29 plus 0.11. We've still got another 23% of people out there, so the probability we get an independent voter then is 0.23. All right. There is no both, there is no overlap, given a Republican, any of that kind of stuff. So let's just start getting straight to the problem. You're conducting this poll, you're making 3 phone calls. Okay, so in those first 3 calls, what's the probability we get all Republicans? So that would be the probability we get a Republican and a Republican, and a Republican. Um, Here's an example where one phone call is not going to affect the other. There's no way that if we call random people at random, if we get two Democrats in a row, we must get an independent or anything like that. Here, it's a safe assumption that each call will be independent of the previous. So we're going to use our multiplication rule. So Republican is 29%, so we're going to do 0.29 times 0.29 times 0.29, which would give us about a 2% chance that we're going to get 3 Republicans in a row. Part B, that we get no Democrats. So the probability of not a Democrat would be 1 minus Democrat, which means there's a 63% chance we don't get a Democrat. So we're looking at not Democrat, not Democrat, and not Democrat. So 0.63 times 0.63 times 0.63, and that's going to be 0.25. So there's about a 1 in 4 shot that on 3 straight calls we don't reach any Democrats. And then the final thing, at least one independent. And remember, when you see that term, at least one, your best bet is to do 1 minus the opposite. So the opposite of at least one independent is no independent. Right. So quick side note, I'm going to make sure I can still see my probabilities. No independent, so 0.23 is the probability of an independent, which means 0.77 is the probability that I do not reach an independent. So we're doing 1 minus no independent, so 1 minus the probability of no independent and no independent and not an independent. All right, so 1 minus 0.77 really to the third. And that's going to end up being 0.699. So there's a 70% chance that we're going to reach at least one independent with our phone survey.